So yesterday when I went and I drew these things, like for instance the tape that encloses the area which the charge that you want to actually evaluate, it's called a Gaussian surface. And so if I tell you to enclose something in a Gaussian surface, that means you basically draw some boundary with which you're going to enclose charge. So if we're looking at a sphere, let me actually open up a new one and go all the way out. So if we look at a sphere and we wanted to know the electric field outside, meaning outside the surface. So this is a sphere radius r. What do? I draw say it's positively charged. So in other words, it has some positive Q. I draw a Gaussian surface. And where do I want to evaluate the electric field? Outside first. Let's say outside first. So I draw a Gaussian surface that encloses the entire charge. Well, what would enclose the entire charge? The sphere, that's right. See? And that's supposed to be a sphere. And what's its radius? Little r. And then we just write Gauss's law. What's Gauss's law say? Q enclosed over epsilon naught is equal to E dot dA. Integral E dot dA is equal to Q enclosed over epsilon naught. So, what's dA? Does E and dA point in the same direction, yes or no? Yeah, right? And there's no angle between them to worry about, correct? So, that's simply going to be what? When you do the surface integral. I didn't actually show you this, but this is actually what the integral looks like. Now, it has that's called a surface integral, which is different than the integrals that you're going to be evaluating in your Calc 1 class. Because really what you're doing is you're evaluating this thing over some type of surface, which is a very different type of integration process if you're going to drill down deep. Yes?
I wanted to ask yesterday, is that E dot dA or E
That's E dot dA. It's a dot product. It's the integral of a dot product.
If there was an angle between,
You'd have to do the cosine between those two. So is E going to be uniform at all points along this Gaussian surface? Yes or no? Yes. So therefore, the integral becomes just a straight up product. It's just E times A. Do you understand why this is the case? Since it's uniform, that means E is constant. So what can you do if something's constant inside of an integral? You can take it out. So it becomes E your sketch.
They had like all these people back in the conference room.
Uh-huh.
It was all official and stuff, and they started talking about like TOK and IB. I'm like, yeah, I'm not in this. So they opened up their sheet. They're like, oh yeah, you're right, you're not. You can go back to class.
Were you an IB?
No, I was.
No, he is an IB refuser.
Yeah.
He is an IB.
yes, isn't all of us?
I'm just an IBCC, which is really safe.
And notice the surface integral, right, is just going to give you A. It's just going to give you the area of the surface. So you just get E times A equals Q enclosed over epsilon naught. And Q enclosed is just Q. But what's A? Yeah, that means surface integral, which is a little different. And technically, it's a double integral because it's over two parameters. But we don't care because, by and large, we're going to be dealing with the simplest cases. If you really go and drill down, it's much more nuanced. Yeah, that means a surface integral. Well, it just means that, like, for instance, if I were to ask you, let's suppose that there is a variable electric field, right? and I were to ask you to evaluate that over this surface, what are you going to have to do? Yeah, like for each point. And so that's not a trivial exercise. Like if it changed on every single point here, I would have to find out. First, I'd have to say that there's a term called parameterization. I would have to parameterize this curve. And then find out the angle between the electric field and each of these points, whatever that electric field pointed, or whatever that function was. But we're not going to be dealing with those types of complex situations. You'll deal with that in Calc 3. In your third. It's, you know, it's more, if you understand it conceptually, then it just becomes more a routine calculation process. It's not that hard, but I'll tell you, it's hard as hell to program that. Yeah, because you would need to actually create an iteration process. It would be pretty nasty to set up that program.
So that's like.
Yeah, that's what a surface integral is. So, and what's the surface area? What is that area which which E is how much? 4 pi r squared. Little r or big R? Be careful. Little r. Why? Because our Gaussian surface is at little r. It's a big sphere. So it's E times 4 pi little r squared equals q over epsilon 0. And notice, what does this give us? The electric field outside of a uniform sphere.
What the heck? That's disgusting.
It's so easy, right? It's so, like, Gauss's law is just evil.
Can you explain how you had a little r squared?
Because that's the Gaussian surface through which we're evaluating E at. We're evaluating E across this Gaussian surface. The whole surface, yeah, the whole surface of that large sphere. That's the enclosed. This is the whole sphere that we're enclosing in another surface. So it's kind of like this. Our Gaussian surface is this imaginary surface that we're enclosing this thing with. Right? It's completely imaginary. And it's out to radius little r. And notice it encloses the entire sphere, which is a big R. And so you're looking at how the electric field dots with this Gaussian surface, this imaginary Gaussian surface outside of it, and then you're evaluating it over the entire surface when you're integrating it. Yes?
What is a Gaussian surface?
Gaussian surface is this dotted line that I'm creating.
What does that represent? Dotted line?
That represents the area through which you're looking at the electric field over. So when I went and I enclosed this, guys, people will not be able to interpret this over your talking. Okay? Here is this full sheet. What I'm doing here is I'm creating a Gaussian surface. And all Gaussian surfaces is basically a snapshot over the area that I'm looking to evaluate it over. And it's a hypothetical construct. Like, for instance, did it have to be here? No, I could have put it here. At the end of the day, what you're doing is you're enclosing the charge through which you want to see the electric field over. So, if you're looking at a sphere, if you want to find the electric field outside the sphere, you enclose the whole sphere in this Gaussian surface. If you're looking inside, what do? So what do we have? We have that the electric field is equal to 1 over 4 pi epsilon naught q over r squared for what region? What region did we just evaluate? So r greater than or equal to big R. And then inside, what would you do? So inside, now we take the same sphere. If we wanted to find inside, where am I going to put my Gaussian surface? Inside. So Now this is inside. The whole radius is r again, but this radius is little r. And so now you do the same thing. The integral of E dot dA equals Q enclosed over epsilon naught. Right? Is E uniform across that Gaussian surface? Yes. So therefore it's going to be E times the integral of dA, which is just E times big R or little r? Little r again. So we have E times 4 pi little r squared is equal to Q enclosed over epsilon naught. But what's different here? Is Q enclosed equal to Q? No. It's going to be a fraction of Q. What fraction? Right? So not the difference, but the ratio of the volume. So it would be Q times V enclosed over V. Is that right? That seems reasonable. And that would leave us with what? Q times which one? Wait, what is this? So it'd be little r cubed divided by big R cubed. Everything else cancels. And so, because all the 4/3 pi cancels, and so what we end up with is E times 4 pi r squared is equal to Q times little r cubed over epsilon naught big R cubed. And what do we end up with? E equals? That's right. Does that make sense?
Yeah.
How can you tell?
Because R is little r is equal to big R.
That's right. So for r less than r, it's 1 over 4 pi epsilon 0 q r over big R cubed. And notice this was so easy. It's like evil how easy it is. No, it's very good. Trust me, Gauss's law is one of those nice miracles. And it's always true, both in electrostatics and electrodynamics. So, realize we're in electrostatics. What does that mean? That's right. We're looking at the steady state. So, and it's not obvious. Like, for instance, if I were to ask you, what is the charge inside of a conductor inside an electric field? What is the field inside of a conductor inside an electric field? What would you say? It's 0, but why? Whoa, be careful. So we're going to get there in a second. Let's suppose I make a uniform electric field. I make a uniform electric field, and I put a conductor in there. So I'll make this conductor with orange. So here's my conductor. And it's just a sheet. What's going to happen?
The electrons will
Which side? Be careful. Which side the electron's going to move?
wait. Yeah, they're going to move that way.
Which way are they going to move? They're going to move that way. Because that's an electric field, right? So what is this? If this was your electric field, and it's very important that I caught you guys on this. This is very important. What does this look like? Like, what would generate this electric field? Line of positive charge, right? So then if I put a positive charge outside that line, which way would it go? That way. All right, so that's good. That's good that you guys... So now, where's the electrons going to go? So the electrons are going to go here. So the electrons are going to move here. And what's going to happen? So it's going to be positive charge here, right? And what happens in that process? Keep going. What's going to happen? What's this creating right here? Its own electric field. All right? And so, and it's the result of the fact that the electrons are free to move. Since the electrons are free to move, what's going to end up happening is that these guys are going to continue moving until what point? Until they stop, meaning, and where are they going to stop? When the electric field is, when the net electric field is 0. So in other words, these guys are going to induce their own electric field because their field lines are going to go like this, and they're going to continue to sort out until the induced field is equal to the external field, so the net field inside is 0. Yeah, and it's just really, really amazing. So that's why the electric field inside of a conductor is 0. All right, who wants to explain it? Try it.
Alright, so like right now, acting on the electron is like the electric field just acting this way, and the electrons going out, and then like the protons are over here, like pulling it a little bit. So it's gonna move over until those forces are equal, and it's like equilibrium. So the electrons are gonna move away until it's active. And the same thing.
Yeah, so like this, it's the protons. Remember, it's not the protons. It's ions. These electrons are being stripped off the metal atoms, right? And why? Because they're free to move. They're free to be stripped off. So they're going to be stripped off, and they're going to move to the left.
And that's why the left side's the negative.
That's right. Because this electric field, how do you visualize this electric field? What caused it?
Positive that side, negative.
Doesn't necessarily need to be negative on this side. It could just be positive here. You just imagine it's just a single play of positive. But yeah, if it was negative there, then it would definitely do it too.
So that strength is larger than the whole field.
What is this?
You said it's moving that way, so that means.
So the electrons are going to move this way, right? Because it's this field up here was generated as if it was just a line of positive charge. All right, so it's going to draw the electrons to it. Well, what's the result? The result is this becomes polarized. And since it became polarized, that means it's going to have its own electric field. Well, as what's going to end up happening is that this is going to continue drawing electrons until what point? The electric field inside here is precisely balancing the external electric field, and there's no movement.
It wouldn't go through like a simple harmonic motion.
No, because it's not. This is constant field. If it was a time-varying field, then you would have.
Well, because it's like a displacement varying field.
If
as it gets closer to that wall of protons, it gets stronger. And as it gets further away from that.
But it's going to reach some equilibrium. Like there's going to be a definite equilibrium. And realize, do you know what time periods we're talking about this happening in? Yeah, we're talking like nanoseconds. So fast these things reach that the electric field goes to 0 inside of a conductor.
What is it that like stops it from like what, you know what I mean? Like what's the retarding force that causes it?
Well, what's technically, I mean, you're asking a good question because
when it reaches equilibrium, it has like a velocity, like with like the spring.
I think it probably is boundary constraints of the material. Like in other words, it can't leave the material. But you're asking much deeper questions, like because you're getting to the point that you can't really have equilibrium inside with electric statics only. But let's hold that off because what I'm trying to actually draw here is this that when we talk about electrostatics, what are we actually referring to? Are we referring to the process by which these guys separate inside of a conductor? No, electrostatics only refers to this end product when the charges are no longer moving. So we can't have moving charges, by and large, in electrostatics. So is that clear? We'll get back to conductors at the beginning of the next unit. But since they form such an important part of electrodynamics from a conceptual standpoint, it's worth going and revisiting it from time to time. So now, going back to Gauss's law, what do we have? So we're done the sphere, we've done the plane, and now we do the line. And so, what do you think the line's going to look like? So the sphere, the plane is planar symmetry. You enclose the plane with the Gaussian surface. What do you think? The sphere is spherical symmetry. So this is going to be? Careful. Shoot.
Are we concerned that line has, it's actually a line of one dimension, or it actually has infinite, minuscule volume?
You're assuming that basically this thing has a minuscule volume, or like a minuscule areal depth.
So it's not like in one dimension, it's basically conceptual.
Yeah, it's remember a lot of these results are extrapolations of, you can imagine it's just being a line of copper, right? That copper, yeah, it has actual volume, but by and large, the one that really we're concerned about is the line itself. So what am I going to do? Where's my Gaussian surface here? Would it be A? Cylinder. So, yeah. Okay? So this is cylindrical symmetry. Yeah, and what you would do is, you could just enclose a portion of it. Because at the end of the day, what electric field are you concerned with? Yeah, the radially outward. So, here's your E. And notice, we can look at this as two separate areas. The one area is the surface of One area, one area is this surface, and the other area is the ends. But what is E dot dA for the ends? That's right. Right? Your electric field's pointing outward from this infinite line, right? And the areal vector is pointing perpendicular to that. So E dot dA is 0. So these ends do not contribute. Ends do not contribute. So the only thing that actually contributes is the electric field. So the only thing that's going to contribute is the, I don't know, what would you call this? The sleeve on the soda can. Perfect. So what do we have? What's dA? Let's say this is L. This thing has length L. How do I find the area of the sleeve of a soda can? It's L times the circumference. So it's E dot dA. Is E uniform? Yeah. Equals Q over epsilon naught. And so what's dA? 2 pi RL. So we have E times 2 pi RL equals Q over epsilon naught. And so therefore, E is E equals Q over 2 pi epsilon naught RL. But a lot of times, notice L is infinite, right? So a lot of times you're looking at this in terms of lambda. So what's lambda equal to? Yeah, it's a linear charge density. So it would be Q over L. That's right. So in terms of lambda, what does this equal? Lambda over 2 pi epsilon naught r. And there you go. Notice how easy that is. It's just incredible. Yeah. That means I'm done. Yeah. If this was a cylinder, that's a good question. If it was a cylinder, what would you have to do? So you're asking a very, very good question.
Can you say that like every point of L would be a disk, and then the charge would be calculated from the center of the disk?
Okay, so now, if I'm correct, let's suppose it's an infinitely long cylinder. Okay? So if it's an infinitely long cylinder, why am I saying infinitely long cylinder? Because what am I trying to do? Eliminate the end pieces. I don't want to have to deal with the electric field that's associated coming out of the ends. I want all the electric field to come out of the sleeve of the soda can. So I don't know what you would call this thing, like the cigarette roll or whatever. I mean, it's like the pumpkin roll. I don't know what you'd call it. The log, the Yule log. That's right. It's the Yule log. All right. So, so what would you do in the case of a cylinder? Let's say it has a uniform volume density. If you wanted to encase the whole thing, you would do a bigger cylinder, right? What do you mean?
Like with the sphere, you can act as if the charge is just coming from the center, like from the center of charge. Like
Correct.
Can you do the same thing with the cylinder, where it's like a line in the middle?
Yes, but this what this means is if you wanted to find the field inside, you would do this.
Oh, inside the cylinder.
You would actually go and make a Gaussian surface inside. It would have to keep cylindrical symmetry. You need that cylindrical symmetry. You wouldn't use spherical symmetry for a line. So for inside, you would make a Gaussian surface inside. For outside, you make a Gaussian surface outside. You guys want some time to work on problems? Because we're done Gauss's law. And so let me see your problem set. Because I want to see at least 15 minutes where you guys can actually work on a problem. So they'll ask you. They'll ask you straight up to do this. Yeah. Like for instance, you could do that for, like you can do that for number 8 again, if you wanted to. And really, a good problem is number 4. Try for number 4. There it is. For our project? Can you use the school what? School numbers. I would rather not. Okay. Just because you may actually have to deconstruct it, and then you... There's also that you probably could purchase one on Amazon for half the price that you would be forced to purchase it if you broke it.
Right, okay. That's true.
Because we have to go through very specific vendors who charge us egregious prices. Because we have to go through specific vendors.
All school stuff, right?
Yeah, all school, yeah. Yeah. Hello? All right, so. All right, I'm going to go through this. Just to make sure everybody's got this right.
Tower ended up held home in 205.
That's crazy.
We had like Oh, shoot, what was the ratio? It was like 11
Uh,
to 1.
yeah, it's 11.1 pounds to 1 gram.
All right, so I'm going to draw the cylinder. That's awesome. So here's a cylinder. Let's do outside first. Outside or inside? What did they ask for first? So inside, I'll take a Gaussian surface. Okay. Remember, this is an infinitely long plane, so who cares? What? You know, what I mean is like, don't worry about the endpoints or how long this thing is. I mean, at the end of the day, you like to be able to exploit symmetries. You know, it's. There we go. All right, so, okay. This has radius r. This is radius big R.
Yeah, big
They
R.
have the other way.
Oh, wait, no.
I'm doing inside.
Oh, yeah.
Focus, guys. So what we have is E dot dA, integral E dot dA is equal to Q enclosed over epsilon naught. Q enclosed is going to be rho times volume enclosed over epsilon naught. But remember, it's only that simple when rho is constant. If rho wasn't constant, what would you have to do? You would have to integrate rho over the volume, over dV.
Are you like foreshadowing?
Yeah, because there's other problems. There's other problems where you do have to do that.
Okay.
So what do we have here? The area with which you're evaluating it over is 2 pi little r L. The volume enclosed is what? What's the volume enclosed in our Gaussian surface?
2 pi little r L.
Be careful.
Squared.
Pi little r squared L over epsilon naught. And so we got massive cancellations. Pi's are gone. R goes with r squared. L goes with L. And we end up with E is equal to rho r over 2 epsilon naught. And that's for r less than big R. Then we enclose this in a bigger cylinder. Let's write out Gauss's law again. Now we're going to call this little r. I'm going to zoom out. And so we have integral of E dot dA is equal to Q enclosed over epsilon naught. Our Q enclosed is simply going to be rho times the volume of the sphere, or the volume of the cylinder.
Which cylinder?
Well,
The actual one?
the actual one.
Okay.
Because that's the actual, there's no charge out here beyond big R. Correct? Like there's no charge outside.
I'm getting it now.
Outside that cylinder. So what we have here, dA, E dot dA is going to be E times 2 pi lil RL. Notice it's lil RL. Why? Because the Gaussian surface is where you're evaluating the electric field. On the right-hand side, we have rho times pi big R squared L over epsilon naught. And so therefore, E is equal to, outside is going to be, pi's are going to cancel, L's are going to cancel. You get rho big R squared over 2 epsilon naught lil r. That's right, it's 1 over r. So what we have, if we're going to graph this, it looks like this. It's linear, and then it's 1 over r. 1 second. Little heads up. For those of you that know a little bit of calculus, what does that tell you about the electric potential? We don't know that yet, right? We'll get there. It's going to be a natural log function. It's going to be logarithmic. We'll see this shortly. E dot integral E dot dr. It is the change, the electric potential is the electric potential energy per unit charge. So,
When we have to integrate big R as well, like, like you were just mentioning how we like rho was a constant.
yeah, so in the case of big R is what you take the integration from and to.
Yeah.
Like if you're going to integrate over the whole volume, you'd start off at little r goes to 0 and integrate out to the maximum.
Okay.
You'd integrate out, because generally for this you would be cylindrically symmetric, so you would integrate out bigger and bigger cylinders. Yeah.
I have a question. If we continue that function such that r, the little r, is the value of r squared, then wouldn't that function reach a constant value?
No. That electric field, think about this. This electric field, you know that if you go out to infinity, what should the electric field be? 0. That's right. That's going to go to 0. All right. How much time do we have?
Like 2 minutes.
2 minutes? All right. So now, at this point, let me look at your problems, because I'm going to assign some problems for you guys to do. And remember, only do up to the things that find electric fields. Anything that involves an electric potential, don't do it. All right, number 5. Number 5, A, B, C. Yeah. I think you might be able to do all 5. I'm not certain, but I'm pretty sure you can do all 5. Electric flux is what E dot dA is.
Oh. That's
Whoa. All right, so a little heads up. Just so this reminder, what is the flux equal to? Whoa. What is the flux? What is electric flux, guys? That is? That is what this is. It is the flux.
Okay, that makes sense.
It says the flux, Gauss's law says the electric flux is equal to Q enclosed over epsilon naught. Well, that's one way to calculate it. Another way to calculate is finding integral E dot dA. So I think you might be able to do 7A. I would go back and try 8 based on Gauss's law. I would try 11, A and C. I mean, listen, at the end of the day, you just do it. Just do what you need to do when you need to do it.